Hi, welcome to a special video on the introduction to spectrometry and Beer's law. And this is on page 576. It's a small section of your book. It's called A Closer Look. So a little bit of an introduction. Many solutions have distinct colors, and you can measure the amount of light it absorbs or transmits at different wavelengths of the visible region. So here you have your white light coming in, and it might absorb or transmit different colors, and then you analyze what comes out. So here, when you're shining your light through, the solution here is blue, and you see blue because blue light transmits through it. So the intensity of a color is an indication of the concentration of the solution. The more concentrated it is, the darker the color. So you can use a spectroscope or a spectrometry to actually measure concentrations. It's a quantitative method of studying matter. Studies the amount of light that is either transmitted or absorbed by a piece of matter. So we use a spectrometer, where here's a picture of one. This is not the exact one we have at our school, but this is a little bit more deluxe one. And this is called a Cuvette. It's like a rectangle little container that you fill with a liquid. It is clear, and the dimensions are 1 centimeter by 1 centimeter. So you measure the absorbance or transmissions of light as a function of wavelength. So you're going to shine your light through this cuvette that's in this machine, and they're going to measure what comes out. So a general procedure, your sample is placed in the cuvette. Light of the selected wavelength is passed through the sample, and the instrument measures the relative amount of light that is absorbed by the sample. Actually, I'm going to go back to that for a minute. Before you put your sample in here, so most of the time your sample is a solution, which consists of a solvent and a solute. So you have to calibrate your system. So the first thing you're going to do is fill your cuvette with just the solvent. So you have your container here, and you're going to fill it just with the solvent. You're going to put it in the machine and measure the absorption, because we don't care about the solvent. We really just care about the solute. So you do that first to kind of calibrate it. Then you're going to add your solution in, stick it back in the machine, and measure it. And now you'll just see the change that occurs. So here's kind of what's happening inside the machine. You have a light source, and it goes through a prism. It separates the wavelengths. It goes through the cuvette. Remember, this is 1 centimeter long. And then you have your sensor that'll pick up how much light is coming out. It amplifies it, and it'll give you a absorption reading. There's two ways of reporting this. You could have percent transmission, which is the intensity of what comes out divided by the intensity of what you put in, times 100, or your absorbance. And you see here the light coming in and coming out. You have less. You're always going to have less light coming out because some of it gets absorbed. So your control. Other compounds in a solution or the solvent itself might absorb at the same wavelength as the compound being analyzed. So this would make your analysis very complicated. So you want to pick a wavelength where only your solute will be absorbed, not necessarily your solvent. But also, as I said before, you're going to run a sample that just has your solvent in it. So you want to run what's called a reference blank, and in here you're going to have everything found in the solution of the sample except the solute or the substance that you're interested in. Okay, so basically you're just going to have the solvent in there, and you're going to use it to calibrate, and you should get an absorbance reading of 0 when you just have the solvent in there. How do we know which wavelength to choose? So you kind of have to run the full visible spectra through your sample and see where you have the most absorption. And that is the wavelength that you want to analyze at. So in this case, you see your maximum wavelength is roughly 450 nanometers. So first you do a scan to kind of see where it's absorbing light, and then you're going to pick the most intense peak. What color light would you use to analyze this compound? Well, this 450 is like violet blue light, right? What color does the solution appear to the observer? The color your solution will appear is the light that is not getting absorbed, but that is actually traveling right through, and that is in your greenish yellow range, which is like right here. That's getting transmitted through, so your solution will look greenish yellow in this example. So what is Beer's law? Beer's law is a relationship between the absorption or absorption of a solution and its concentration. The higher the concentration, the more light it's going to absorb. So the amount of light absorbed is proportional to the concentration. Okay, so here we have this equation where A is your absorption or absorbance, and little a is a constant that you have to determine experimentally. B is the length of the path the light travels through. And in this case, we're using those containers called cuvettes. And I don't know if you remember what this dimension is here. Remember, the light's going to go through 1 centimeter. So in this case, the path of the light is 1 centimeter long. Okay? And C would be your concentration. So if you are measuring in a spectrometer, you're going to get the absorption. You know that your cuvette is 1 centimeter. And say it's a solution you made, you know the concentration, you can figure out this constant here. But this is not something that you could easily look up. So what does this tell us? There is a direct relationship between absorption and concentration. So you prepare solutions of known concentrations and you analyze their absorbance at this maximum wavelength. And then you're going to plot the absorbance here on the y versus the concentration on the x. And you should get a pretty straight line, but you're going to curve fit it, and then here you have your relationship. This r squared is a statistical value that shows you how good your curve fit is to your data. The closer this value is to 1, the better your curve fit. Okay? So in this y equals mx plus b equation here, x is your concentration and y is your absorbance. So if I gave you an unknown solution now, you can measure its absorbance and come across on the graph, come down, and find out its concentration. Since a is a linear function of c, we could use this y equals mx plus b, and we're going to relate it to a equals abc. These two are equal, and these two are equal. So your slope is basically a times b. Remember, b in our case is 1 centimeter because our cuvette is 1 centimeter. So using a spectrophotometer and Beer's law to find the concentration of an unknown. So what do you have to do? One, you have to make a graph. So all done at the maximum absorption peak. Okay. So you prepare a standard plot. So you plot your absorbance versus concentration for various standard solutions. And then you determine your best fit line. Remember, you're going to plot concentration on the x and your absorption on the y. You can ID an unknown concentration because you can measure the absorption, and then you could kind of, so say you could come across here, come down, and measure the concentration. So this is very powerful. So here's an example. Use the plot to determine the concentration of a solution that has an absorbance of 0.25. So you go up here, 0.25, you come across, You see it's crossing over here, which is roughly 0.0072 moles per liter. So you could do it that way off the graph, or you could use this, where y is equal to 0.25, and then you solve for x. And that is the end of our beer law.